Before the first shovel ever hits the ground on any huge project today, a perfect digital twin of that site already exists. From skyscrapers to massive bridges, these modern marvels are built first in the virtual world, all thanks to hyper-accurate data. So today, let's dive into the incredible technologies that let us capture our world with millimeter precision. But how is that even possible? Really think about it. How can teams of engineers, often spread across huge and difficult terrain, place every single steel beam, every concrete foundation with a certainty measured in millimeters? Well, the answer isn't one single gadget. It's a really sophisticated workflow that merges data from space, from the ground, and from the air. So to really get this, we're going to break it down. We'll start with the global foundation, the satellite systems. Then we'll zoom right into the project site for that ground-level precision with lasers. After that, we'll take a look from the sky. And finally, we'll see how it all comes together in the digital world. All right, let's start our journey. And we're beginning hundreds of miles above the Earth with the tech that provides the fundamental coordinate system for every single modern survey. So you've definitely heard of GPS. Well, GNSS is the official umbrella term for all those satellite systems. At its heart, it's basically a global utility. You have this constellation of satellites constantly broadcasting signals down to Earth, which lets a receiver on the ground figure out its exact three-dimensional position, that's your X, Y, and Z, or latitude, longitude, and altitude, anywhere on the planet. The way it works is actually pretty simple, but incredibly powerful. A receiver on the ground is just listening for signals from several different satellites. By measuring the exact time it takes for each signal to travel from the satellite to the receiver, it can calculate its distance from each one. And once it has signals from at least 4 satellites, boom, it can pinpoint its exact location using a process called trilateration. Okay, so for any real-world engineering project, GNSS is the absolute foundation. Before any work even starts, surveyors use it to set up a network of high-accuracy control points all across the site. Think of this network as the master reference grid for the entire project. It guides everything from the center line of a new highway to the foundations of a new building. Now, this brings us to a really crucial point. The GPS in your phone is great, but it's only accurate to a few meters. For professional work, that's not nearly good enough. Surveyors use a technique called real-time kinematic, or RTK. This uses a second, stationary receiver on a known point to correct for atmospheric signal delays in real time. And the result? It boosts the accuracy to an incredible 1 to 2 centimeters. That's the game changer. All right, so our site-wide control is now locked in. The focus now shifts from centimeters down to millimeters. We need that fine detail for the actual construction. And this is where the ground-based instruments come into play. So, meet the absolute workhorse of the construction site, the total station. This device is an engineering marvel. It basically combines a super accurate digital protractor, that's the theodolite part for measuring angles, with a laser distance meter, or EDM. And it's all hooked up to a powerful little computer right on board. In the field, a surveyor will aim the total station at a reflective prism held by a colleague. With just one press of a button, it shoots a laser, measures the angle and the distance, and instantly calculates the precise 3D coordinate of that exact point. And the modern robotic versions, they can actually lock onto and follow the prism automatically, which means a single surveyor can lay out hundreds of critical points in a day. And this is the level of precision we're talking about. When you're marking the exact corner for a building column or aligning a massive steel beam, there is just zero room for error. The total station delivers accuracy down to just a few millimeters. It's how you ensure the digital design gets built perfectly in the real world. But what if you need to capture an entire existing building or a complex bridge, not just single individual points? Well, that's where LiDAR comes in. Instead of one laser pulse at a time, a LiDAR scanner sends out millions of them per second in every direction. It measures the return time of every single one of those pulses and uses them to create this massive three-dimensional data set we call a point cloud. Honestly, this technology is transformative. It lets us create perfect digital copies of existing structures, which is absolutely critical for renovation projects and for creating building information models, or BIM. Those incredibly detailed 3D models that are used across a project's entire life. The precision is so high, it can actually be used to monitor a bridge for tiny amounts of movement or even map the true ground surface hidden underneath a dense forest. So, we've covered global positioning and we've covered ground-level detail. But for really large projects, like a new highway or a huge land development, trying to survey that entire area on foot would take forever. So we need to get airborne. Drones or UAVs have just completely revolutionized large-scale mapping. It's that simple. In just a few hours, a single drone can fly a pre-programmed grid pattern over a massive site. It captures data that would have taken a ground crew days, maybe even weeks to collect, especially if the terrain is difficult or dangerous. And the data they produce is incredibly rich. We're not just getting photos here. The software takes all the overlapping images and stitches them together to create what's called an orthomosaic, a single high-res image that's perfectly scaled and geographically accurate. But even more importantly, this process generates detailed 3D models of the ground. These are critical for everything from planning drainage to calculating the exact volume of dirt you need to move for construction. Now, the type of sensor you put on the drone is a critical choice. It really depends on the job. Photogrammetry, which just uses a standard high-res camera, creates these beautiful, visually rich, full-color 3D models. But aerial LiDAR has a huge advantage. Its laser pulses can actually punch through vegetation to map the real ground underneath. It can also capture really fine geometric details like individual power lines that a camera might just completely miss. Okay, we have now collected terabytes of data from satellites, from lasers, and from drones. But all of that raw data by itself isn't the final product. The last and maybe the most critical step is to bring it all together. This is where incredibly powerful platforms like AutoCAD Civil 3D or ArcGIS really shine. They act as the digital hub where all these different data types, the GNSS control points, the total station measurements, the LiDAR and drone point clouds, are all imported, aligned, and processed into one single, cohesive digital model. And this right here, this is the stuff that engineers and project managers actually use to make critical decisions. The software is what generates the final topographic maps showing elevation contours, the official boundary drawings for legal records, and those detailed 3D surfaces that are used for design and analysis. So when you look at it all together, this integrated workflow is a very clear sequential process. You start macro. Step 1 is using GNSS to establish that global site control. Step 2, you refine the detail with total stations for all the critical features. 3 and 4, you capture the broader site with drones and LiDAR. And finally, step 5, all that data is synthesized in the software to create the authoritative digital twin, with each step building on the precision of the one before it. The impact of this system is just immense. It massively boosts productivity on site, it significantly reduces the potential for really expensive human error, and it provides that extraordinary level of precision that modern mega projects absolutely demand. And crucially, this digital twin doesn't just stay with the surveyor. It integrates seamlessly into the larger BIM workflow, giving valuable information to architects, engineers, and construction managers all the way through the project. So, we've created a near-perfect digital copy of our world. We can build from it, we can analyze it, we can run simulations on it, and that leads to the final, really big question. As this technology gets even more powerful and happens more in real time, what new possibilities will open up when that line between the physical construction site and its digital twin all but disappears?
If you're ready to level up, like and share this video. Subscribe and hit the bell to join the future of efficiency. Aera, your life,